Um, Good afternoon, everybody. So thank you for coming today. So our speaker in the seminar today is Dr. Sarah Wright, that is astronomer at the South African Astronomical Observatory. And she will talk about AGNs and their radio emission. So you can start now, Sarah. Thanks.
Thank you. Yes, Sanibonani Mulweni. Hello, everyone. As just mentioned, my name is Sarah White, and I'm an astronomer at the South African Astronomical Observatory. And thank you very much to Edwin for the invitation to give this seminar today. So I'm fascinated by active galaxies, and I've studied them at multiple wavelengths. And in today's talk, we're going to focus on what we can learn about these sources through their radio emission. Sorry, there we go. So just a brief outline for the talk today, making sure that we're all on the same page, that we understand what is meant by an active galactic nucleus. And then kind of the main part of the talk will be describing a sample of the brightest radio sources across the southern skies. This is known as the Gleam-Podjansky sample. And I'll be showing some examples of radio sources that don't follow the usual power law description in terms of their synchrotron emissions. So by building up these broadband radio SEDs, we can start to learn more about the physics within these sources. And I'll also present some MeerKAT observations, most of them not as new, but still ongoing observations are being built for the sample. And then in the final part of my talk, I'll be describing more recent work on the radio quiet population of the, in terms of AGN. And this is just to bear in mind, for those not familiar with this term radio quiet, it doesn't mean that they're radio silent. They just have relatively low levels of radio emission. And it's important that we consider how those sources also contribute to the way in which galaxies evolve over cosmic time. So first of all, just make sure we're also helping those who are not as familiar with different parts of AGN studies. Of course, mostly we would focus, well, in the past, there's a lot of astronomy that's been conducted in the visible optical part of the electromagnetic spectrum. But radio astronomy has kind of undergone a resurgence over the past few decades. And I wanted to just show this to illustrate the wide window that we have in the radio part of the spectrum. And that means we have awesome opportunity to observe our sources at multiple radio frequencies, and so build up a more complete understanding of these sources. And of course, we're familiar with looking up at the night sky, and in the optical visible part of the spectrum, we tend to see just these point-like sources. So these are all stars or planets in our solar system. Or if we're lucky, we can also see the faint emission of galaxies. But of course, we tend to need much larger optical telescopes in order to detect faint optical emission. Now, this screenshot is taken from a very nice outreach tool called the Gleamoscope. And as you can see in the top right corner, you can scroll between different parts of the electromagnetic spectrum to see how the same patch of sky changes at those different wavelengths. So if we scroll down to the radio, this image is taken from GLEAM. So this is an all southern sky survey conducted with the Murchison Wide Field Array, which is a low radio frequency telescope in Western Australia. And if we focus on this particular source here in the optical, we can see that associated with that source is this very extended radio emission shown here. And this particular source is called Centaurus A. And nearby, you can also see another extended source with 3 peaks in the radio emission as shown here. Now, as you may have noticed, going between the optical and the radio, in the radio, we have much more extended sources, and we also can detect many more sources because we're not affected by dust obscuration, which is a problem for optical astronomy. So in the radio, we can actually build up a much more complete picture of how galaxies evolve if we select our samples in the radio. And so to help explain, well, why do we see this extended radio emission for some sources? So this boils down to a subset of the whole galaxy population we tend to call active galaxies, active galactic nuclei. So this is where we have gas material that's falling onto the supermassive black hole at the center of the galaxy. And as that takes place, we have a large amount of emission being produced over a wide wavelength range. And that means that that offers many avenues then for selecting our AGN samples. And surrounding that accretion disk, we have something that's known as a dusty torus. That's illustrated here. And it's that dust that, if we happen to be viewing an AGN at a particular angle, in the optical, we may not see it at all, but in the radio, we do. And also to bear in mind that in about 10% of cases of AGN, we have the production of these powerful radio jets as illustrated here. And we have all these different terminologies for how we classify these sources, with the term blazar being where we're looking down the radio jet axis. So that's something that I'll refer to later in the talk. So why do we care about active galactic nuclei? Well, ultimately, we want to understand how do galaxies evolve over cosmic time? How does the black hole accretion influence star formation in the
You tell me, what can I say?
I think I can hear someone in the audience who hasn't muted. Could you please mute? Thank you. And in order to understand how these AGN interact with their surroundings, it's important that we observe these sources, as mentioned, at different radio frequencies. And that gives us also different an understanding of how these sources interact at different spatial scales. So at low frequencies, we can see the very extended radio lobes associated with this particular radio galaxy. This is Virgo A, also known as M87. And at higher frequencies, we can kind of zoom in and get a better understanding of the structure of the radio jets that are emanating from the supermassive black hole at the center. And then we can go to higher resolution still if we make use of very long baseline interferometry. So that gives us this image shown here with the VLBA. And as you may remember from a few years ago, we had the very first observation of an accretion disk surrounding a supermassive black hole, and that was from the Event Horizon Telescope. So this gives you kind of an overview of how we can link our understanding of the physics around a supermassive black hole to how those jets interact with their surroundings and influence possibly the star formation in their host galaxy. And as mentioned before, the beauty of radio observations is that it gives us that unbiased view of the universe. We can detect all of the star formation that's taking place and all of the AGN activity that's taking place. But then, of course, because both of those processes produce radio emission, we have to think carefully about how we disentangle those two contributions to the total radio emission. And we note that as we go to lower radio flux densities with next generation radio telescopes, including MeerKAT, we're moving away from a regime that's dominated by AGN and into a regime that's dominated by star formation, so we think. To note that these observations, if we compare them to, for example, simulations by Willman et al., within this bump at lower radio flux densities, so below about 1 millijansky, it's not just star-forming galaxies there. There's also a contribution from those radio-quiet quasars. And a quasar is a particular type of AGN where the accretion of material onto that supermassive black hole at the center is taking place very efficiently. So for the remainder of my talk, first I will consider the AGN that we have at the radio bright end of this distribution, and then return to the latest work that's being conducted at the radio faint end. So given how many AGN samples there are out there in the literature, why is it valuable to select our sources at low radio frequencies? Well, at low radio frequencies, the emission tends to be dominated by those radio lobes associated with the radio jets. And those lobes are not affected by a phenomenon known as Doppler boosting or relativistic beaming. And that means that we don't have an overabundance of sources where the radio jet axis is close to the line of sight. So that beaming tends to push sources above the detection level, like artificially. But if we consider the low frequency observations, then we can create a sample that's free of this orientation bias. Also, by constructing these broadband radio SEDs, we can get a better understanding of the physics taking place in these sources, which I'll come back to later. And also, selecting at low frequencies is important if we want to have a full picture of the different life cycles of these AGN. And that's because as radio emission ages, it moves to lower frequencies. And so we may find that we are actually detecting AGN that only show AGN activity signatures in the low frequencies, at the low frequencies, sorry. Whereas there's no indication at other parts of the electromagnetic spectrum. So again, this allows us to build up a more complete census of how those AGN are interacting with their surroundings in terms of the lifespan in which that interaction takes place. In the same way we consider star formation histories of galaxies, we also need to consider black hole accretion histories of these galaxies. So, having established why the low radio frequencies are so important for our sample construction, the Gleam-Forjansky sample is a compilation of nearly 2,000 of the brightest radio sources across the southern sky. This is, as mentioned, thanks to a survey called GLEAM, conducted with the Murchison Wide Field Array. And here we have a histogram of the radio brightness of these sources. And to the right of this vertical line are the types of sources that we're already more familiar with, thanks to the famous 3CRR sample of the Northern Hemisphere. And sorry, I can hear someone in the audience again. But with the Gleam-Forjansky sample, because we have this lower detection threshold and also covering a larger portion of the sky, we can detect sources that are of intrinsically lower radio power and also at a higher redshift. And the reason we want this sample that's 10 times larger than 3CRR is so that we can study the radio properties of these AGN as a function of redshift and environment. And that's important if we're to truly understand how are these radio jets actually, how do they form in the first place? Does it depend on the amount of gas that's in the environment that's able to fuel them? Does it depend on possibly the spin of the supermassive black hole? We don't know. And so this is important for comparing to simulations as well. We need to build up these large sample statistics in order to get a more complete and representative understanding. So just briefly, it's kind of a flowchart to describe all of the work that went into creating the Gleam-Forjansky catalogue, which has been publicly available since 2020 now. And as you can see, we've combined the Gleam data, which is, gives us 20 Gleam flux densities at low frequencies between 72 and 231 megahertz. And combining Gleam with other radio surveys and all-wise in the mid-infrared and some optical data from 6-degree field galaxy survey, we did that crucial work of determining the radiomorphology of these sources and exactly where is the host galaxy that hosts that radio emission. And that's crucial if we want to combine these multi-component radio catalogues with information at other wavelengths. We need to be absolutely sure that we have the correct host galaxy for that radio emission. So all of the kind of nitty-gritty details for this catalogue creation can be found in paper 1, and all of the additional literature checks to ensure high quality of this catalogue are all described in paper 2, which we refer to as the Hitchhiker's Guide to the Southern Radio Sky. And in addition to those multiple flux density measurements in the radio, we also have calculations of spectral indices, and crucially, as mentioned, those host galaxy positions for about 86% of the sources in this version of the catalogue. So why do we want to build up these broadband radio SEDs? We already have these low frequency measurements and also some measurements at around 1 gigahertz. Well, first of all, we can measure, it allows us to measure the spectral age of these AGN. Remember that if we have a continuous injection of electrons into the magnetic field, then we have synchrotron emission being produced, and this is the spectrum we would see for a single electron. And the superposition of those spectra for individual electrons gives us this overall power law function here. And that's represented by this navy blue line in the lower part, in the lower figure. And note that if we switch the AGN off, we no longer have that injection of electrons into the surrounding medium. And so the radio spectrum takes on a more and more curved appearance over time, as illustrated by the color scale on the right here. But note that we also need to make sure that we know the redshift for these sources in order to break the degeneracy in terms of the spectral curvature of these active galaxies. So a very worthwhile spectral signature that we can get from building these broadband SEDs is it allows us to look for restarted radio galaxies. And why is that? Well, with this particularly extended source in the GLEAM survey, we can consider the individual radio spectra for the lobes. So those are the red and blue data points shown here. And also the data, the radio spectrum just for the radio core at the center where the supermassive black hole is. And those are the green data points shown here. So we can see that for the core, we have this very kind of flat radio spectrum, but for the lobes, we have this steep spectrum shown here. And overall, we have a spectrum that shows a steep part in the distribution low frequencies, and it flattens out towards higher frequencies. And so you can see that a spectrum curving like so is a signature for these restarted radio galaxies. And why do we say that this particular source is restarted? Well, note that those radio lobes here are in the plane of the sky. Of course, we're dealing with a 3D object, but a two-dimensional projection. But more recent observations, as found by Hernandez Garcia et al., they reclassified this source as a blazar. So as mentioned before, that's where we're looking down the radio jet axis. So if that's the case, then the radio jet axis must have changed from the time it produced these extended radio lobes from to a time more recently. And so that gives also, just a reminder that we also have this time evolution in terms of understanding the AGN activity. And for the whole GLEAM-4 Jansky sample, it's interesting to compare, well, what is the spectral index at low frequencies to the spectral index at higher frequencies? As mentioned before, the sources that are curved like so in the top left of this figure are sources that tend to be, we believe to be restarted AGN, and sources with a radio spectrum that curves in the opposite direction are shown in this part of the spectrum. And for those, we can actually determine the spectral age. Thankfully, thanks to simulations of radio galaxies by Turner and others in their group, we can actually determine the duty cycle of these AGN. And so by that, I mean, how much time does a typical AGN spend in an on state, so that with those radio jets interacting with surroundings, and how much of the total lifespan is spent in the quiescent state. So again, as mentioned before, we want to consider the AGN activity history in addition to star formation histories. And for a subset of these sources, we have follow-up from the VLA to also look for remnant radio galaxies. So those are the sources where we can detect the radio emission from those radio lobes, but with the existing radio images, we don't have a detection of the radio core. So we need to go to higher frequencies, such as 5.5 and 9 gigahertz. And for a subset of the sample, we've extended that radio coverage further still out to 20 gigahertz. And that's by combining information from GLEAM and SUMS NBSS with data from the Australia Telescope Compact Array. This is at 5, 9, and 20 gigahertz. And within this subset of about 200 sources, 3/4 of them follow that usual power law description that we use to describe synchrotron radiation. But in about 16% of cases, we have these peak radio sources, peak spectrum radio sources. And that spectral signature is indicative of a young radio galaxy where those radio jets have not been able to kind of burst through the cocoon of gas that's surrounding the supermassive black hole. In about 8% of cases, we have radio spectra that curves so it's concave shape. And initial checks against the literature show that these tend to be mostly blazars. So again, we're looking down the radio jet axis. But we do need to be a bit more careful in our interpretation here because blazars tend to have a very high variability. So hence the much larger error bars shown here. And then in a few cases, we have Green-Forjansky sources that showed a kink in the radio spectrum at these low frequencies. And note that we would only have been able to identify this unusual behavior thanks to the contiguous coverage provided by the MWA. The downside of that is that the MWA has a very large beam. And so we thought, well, maybe what we actually have here are two unrelated AGN that are being blended together by the MWA beam and giving us this total spectrum. But when we followed it up with MeerKAT, even at the higher resolution, this source remains unresolved. And so it's possible that we have different epochs of activity that have been superimposed, giving us this overall spectrum shown here. It's all very intriguing, and we're looking forward to getting some BLBI follow-up these sources. For 140 of the Green-Forjansky sample, we followed this up with open time on MeerKAT. And this was because, despite all of that, very time-intensive and catalog creation and identifying the host galaxies for these sources, that still was only for 86% of the sample. There were also sources that had more complicated radiomorphologies or just were in regions of the sky where the host galaxy candidates were very densely distributed. And so this is where you need the higher resolution from MeerKAT to be absolutely certain that, yep, this is the position of the accretion disk associated with that supermassive black hole. So that's very satisfying that you can get some really clear, unambiguous host galaxy identifications. For this middle source, we confirmed that this is indeed a head-tail galaxy. So that's where those radio jets have been bent in a direction, in this case, downwards. And in this particular example, that plasma has then joined up again. So that's why we see kind of a hollow here. But unfortunately, in some cases, even with the better resolution from MeerKAT, we still unable to identify the host galaxy. It's unclear here whether we have unrelated sources or where the host galaxy actually is. So this is where we need additional follow-up again. And a reminder that, although we were concentrating on the Green-Forjansky source at the very center, and being so bright, we only observed these sources for 5 minutes each. We still get this amazing coverage from MeerKAT just because of its incredible sensitivity. So a reminder that all of this data is in the SARAO archive as publicly available. You can have a look around and see if you find any more interesting sources that you'd like to investigate. And one of my favorites from the Glean-Forjansky sample out of this MeerKAT subset is Glean-Forjansky 1523. And originally in the lower resolution radio images, we identified this as a Z-shaped source. But as you can see with the MeerKAT contours shown in purple, we can pick out this beautiful helical or corkscrew-like structure. And I've illustrated, I've put side by side with this VLA image of an X-ray binary, SS433. And the reason we get this corkscrew structure is believed to be due to some kind of force that's perturbing the supermassive black hole at the center of the galaxy, causing a precession of the radio jet like so, carving out that helical structure. And so we have a suggestion that we've got the same kind of physics taking place on supermassive black hole scales as shown on the left, and as on a stellar mass black hole scales as shown on the right. And further with this work by my master student, Katleo Sejaki, who's now my PhD student, we wanted to highlight the importance of that host galaxy identification. Note that for the MeerKAT subset, we were focusing on the sources that have the most unusual radiomorphologies. And so it's unsurprising that when we look at the separation between where the actual host galaxy is and where the radio centroid position, so that's the position that's usually quoted in radio catalogs, how offset those two positions can be. For the majority of the Glean-Forjansky sample, so we have this wide distribution here. Within the black box here is this is a linear scale, but beyond this black box, we transition to a logarithmic scale. And as you can see, most of these MeerKAT, the sources that we followed up with MeerKAT are in these outer regions. So we can, can have a host galaxy that's sometimes even 100 arc seconds away from where you might think the host galaxy resides. And so this is just to illustrate that we can't just apply positional cross-matching in order to combine our radio catalogs with information at other wavelengths. And this is another particularly beautiful source that's in the Glean-Forjansky sample. With MeerKAT, we're able to detect these collimated synchrotron threads. And we believe that these arise from electrons actually escaping the radio jets from due to Kelvin-Helmholtz instabilities and igniting dormant magnetic flux tubes which are close to the host galaxy. And what's particularly interesting with this source, in my opinion, is the uniformity of the radio emission within what's referred to as these ribbons. And the idea here is that in the past, the radio jet would have carved out a tunnel in the surrounding medium. It then switched off, but the plasma within that tunnel was able to reach equilibrium, leading to this uniform brightness. And then more recently, the radio jets switched on again. And so hence you have this brightening closer to the supermassive black hole at the center. We also have the indication that it's restarted again from the spectral index map, which is shown here. And what is meant by the rings for this radio galaxy? Well, this is referring to the beautiful filamentary structure within the southern lobe. So what's just really incredible with MeerKAT is that you can actually pick out that structure. And in order to model, try and infer the inclination angle of the this southern radio jet, we assume that as this jet is plowing into the surrounding medium, it develops these shock fronts that are concentric circles, and then we can compare that to the ellipses that we observe, and therefore kind of backwards model the inclination of this source with respect to our line of sight. So this is a very novel technique that we'd love to apply to more radio galaxies, of course. Another part of the follow-up for this sample is, of course, to improve the availability of redshifts. And that's because currently the only all southern sky spectroscopic survey is the 6-degree field galaxy survey. But with this ongoing multi-semester program on the Southern African Large Telescope, we're able to go about 4 magnitudes deeper, and this program is looking at about 600 Greenford-Jansky sources. We have here some examples of salt spectra. We're expecting to see lots of emission lines, but also note that there are many host galaxies that show a combination of absorption and emission lines, and in some cases, well, in many cases actually, only absorption lines. And that's something that we need to also keep in mind if we're using optical surveys for constructing our AGN samples. If we apply a flux density threshold, we're going to tend to pick up more of these emission line sources and miss the absorption line sources, even though they're at the same redshift. So yeah, another caveat for when you're analyzing multi-wavelength data sets for AGN. For another subset of the Greenford-Jansky sample, this is basically the creme de la creme, we say, the brightest of the brightest radio galaxies across the sky. And this is where we've applied a stricter flux density threshold at 9 Jansky, so 178 megahertz, in order to create a subset that's equivalent to the 3CR survey of the Northern Hemisphere. And in total, those northern sources and the southern sources form a catalogue that's consists of 264 radio galaxies. Now, there's been some initial analysis of X-ray observations from SWIFT, so that's archival data. But the idea is that for all of these sources, we want to get complete X-ray coverage in order to understand how those radio jets are carving out the cavities in the surrounding medium. And that's because the X-ray allows us to measure the distribution of hot gas in the surroundings. But as an extra bonus for us, we also can detect the position of the accretion disk. So that allows us to confirm whether we have our host galaxy identification correct or not. And most recently, we have new redshifts for this subset. This is from multiple optical telescopes. And this was necessary because out of those 264 sources, about half of them didn't have a firm spectroscopic redshift in the literature. But with these new observations, we can confirm the redshift for 51 of those sources, and we have brand new redshifts for 42 of them. And so at the moment, the spectroscopic completeness for the sample stands at 71%. And there's additional observations that are ongoing in order to get full spectroscopic completeness. So a reminder, why do we care about AGN again? We're familiar with the kinetic energy that's associated with those powerful radio jets. They can disrupt the surrounding gas, preventing stars from forming. They can also trigger the collapse of a molecular cloud and so promote star formation. But remember that those radio loud AGN are only about 10% of the total AGN population. The vast majority of the AGN population, as mentioned before, are termed as being radio quiet. They're difficult to detect below the typical flux density threshold of most radio telescopes in the past. And it's thanks to deeper radio data with MeerKAT, such as the MIGHTY survey, that we can actually construct larger samples of AGN and compare those radio quiet sources with our radio loud AGN. And why we want to do that? Well, remember, we still have that accretion process that's taking place. So there may not be the powerful radio jets present, but we still have thermal energy associated with that accretion disk. And that can heat the surrounding gas to such a level that stars may no longer be able to form. So this is how those sources can also contribute to the way in which galaxies evolve and grow over cosmic time. So as mentioned, it's very difficult to detect these sources in the first place, and then even more difficult to distinguish how much of that radio emission is from the star-forming regions in the host galaxy, and how much of that radio emission is connected to AGN activity at the center. And this is an area of ongoing debate in the literature, and note that quite often we can be applying the same methods of analysis, but we reach opposite conclusions. And we believe that the reason for that is because it basically comes down to selection effects. How you create your AGN sample in the first place will have a significant impact on the final conclusions that you draw. So, for example, previously, it was just assumed that, well, if there are no powerful radio jets present, then all of the radio emission must be due to the star formation in the host galaxy. And an example that argued for this was that this is a number counts plot, and we can fit a polar function to the distribution of radio loud quasars. But KwaZulu-Natal had to complete a stacking analysis in the MBSS in order to try and detect radio quiet quasars, and could only infer the range and the distribution of those sources. So it still wasn't clear, well, how important are these sources at low radio flux densities? With our deeper data, we were able to demonstrate that, yes, we really are detecting a contribution of radio quiet quasars to this bump at lower radio flux densities below 1 millijansky. And note that they had inferred that, well, if we're deviating away from this power law function, which is used to describe AGN activity, then the deviation must indicate there's some other process that's taking place, and that's why they reached the conclusion that star formation is more important. But this is where the value of multi-wavelength datasets comes in, because we want to understand, well, how much of that radio emission is really due to star formation, how much is due to AGN activity. And so one method is to apply two different estimates of the star formation rate. And in this case, we had one estimate that came from the star formation main sequence, which is shown in the y-axis here. And the other estimate is based on the assumption that all of the radio emission is due to star formation. So if that assumption is correct, then all of our sources should lie on this dashed line shown here, this diagonal line. The fact that we have an offset away from that line is indication that there's some other process that's taking place. And that's where we infer the contribution of AGN activity. And this was a very controversial result at the time, given that everyone just assumed, oh, all of the radio emission must be due to star formation. And we looked at this further by applying the far-infrared to radio correlation to a second sample of quasars. And this correlation arises, it's determined for star-forming galaxies. It arises because where you have stars forming, there's a large amount of dust being created, which re-radiates in the far-infrared. And of course, where you have stars forming, you also have stars dying. And this is, with that, we have supernova remnants, which is over which these electrons are being accelerated across these magnetic fields and producing the radio emission. So we have a very tight correlation that's seen over a wide range. And if we apply that to our sample, well, this is where the far-infrared to radio correlation is. This is where we expect star-forming galaxies to lie. And again, we're seeing quasars to the right. So we can look at the total radio luminosity, subtract the amount of the radio emission that we believe to be due to star formation, and calculate the accretion component. And we find that consider the sources that are detected in both the radio and infrared, that the radio emission from connected black hole accretion is at least 60%. So this is important also.
Thank you.
have this quantification if we're going to actually compare to simulations and understand the significance of that black hole accretion activity across the AGN population. So we would like to look at this in more detail, of course, with the deeper radio data that we have from MITE, and this allows us to go about a factor of 5 than before. Again, please, could anyone who is not muted, please mute so that you're listening attentively? Thank you very much. So we start off by selecting our quasars in optical near-infrared color space. So they occupy this region following previous work by Maddox et al. And White et al. And this is to avoid possible host galaxy contamination. And for the sources that don't already have a spectroscopic redshift in the literature, we have follow-up observations from the Southern African Large Telescope, as shown here. And of course, those redshifts are crucial if we want to calculate intrinsic properties such as the radioluminosity. And as before, we take that radioluminosity and use it to infer an estimate of the star formation rate, again, based on the assumption that all of the radio emission is due to star formation. So that gives us our measurement here. Note that this correlation is from Delhaize et al., which considers the redshift evolution of this correlation. And then as our independent estimate, we have another star formation rate that is based on far infrared data. And as before, where if those two star formation rates are equal to each other, that's indicated by this dashed line here. This is where we expect star-forming galaxies to lie. And again, we're seeing a good fraction of the sources in this part of the plot, in which case we can describe them as being AGN dominated. So the AGN is contributing a more significant component of the radio emission than star formation. However, note that with MeerKAT, we're seeing that this AGN fraction is actually less pronounced than previous work. It's at a level of about 50 to 60% now. And we believe that to be because of the wonderful sensitivity of MeerKAT to diffuse radio emission in the host galaxy. So it's detecting much more of the star formation that's present. So that's very intriguing. And we'd like to look at these sources in more detail. And as a starting point, we have split the sample into 4 redshift bins, as illustrated here. And we find that the percentage of quasars that can be described as AGN dominated is increasing with redshift to around redshift 2. And we believe that that's because, as previously found, we actually have a connection between the optical luminosity and the accretion-related radioluminosity. And that's because, again, we have these selection effects, of course, whenever we create a sample. And this is something that's known as Malmquist bias. So at the higher redshifts, we're tending to pick up more intrinsically optically brighter sources. So we have to take that into account. So we believe that to be that to explain the trend shown here for the first 3 redshift bins. But then we have a significant drop for the final redshift bin. And the reason for this is because, well, based on work by Simeonidis et al., they find that the SED fitting to the far infrared data tends to become more unreliable at the higher redshifts. And that's because most SEDs assume that, well, in the far infrared, all of the far infrared emission is due to star formation, but actually there's an increasing fraction of that emission is due to the AGN. So we don't really have an independent estimate of the star formation rate anymore. And that means if we're overestimating the star formation component, then we're underestimating the black hole accretion component. So the data points for this highest redshift bin should really be taken as lower limits. Right, so extending this work further, we have relaxed the criterion that these quasars should lie in this area of optical near-infrared color space. And by removing that criterion, it means that we're not just looking at unobscured quasars. So those are the sources where we don't have the accretion, the dusty torus along our line of sight. We're also including obscured quasars. And here we have a histogram that shows the radio flux density measurements for those obscured quasars and unobscured quasars. And for the whole sample, we have extracted radio flux density positions at pseudo-random positions in order to try and quantify the noise level in those radio maps. And remember that the noise is a contribution of the thermal noise set by the sensitivity of the radio telescope, and also the confusion noise, which is set by the maximum baseline of the radio telescope. So I'm very much looking forward to much longer baselines so that we have higher resolution radio images and can also help to lower this noise threshold and detect more of these radio quiet sources. So we've looked at this in more detail by splitting the sample as a function of stellar mass and as a function of redshift. And note that for stellar masses, these are more reliable for the obscured quasars. And that's because we're actually, the torus then becomes quite helpful because it's blocking the optical near-infrared light from the accretion disk, leaving us just the optical near-infrared light from the host galaxy, which is what we need for deriving these stellar mass estimates. So this will give us more reliable results. So we've restricted that quasar sample to just those obscured sources along the x-axis. Shown here is the redshift, and the stellar mass shown along the y-axis. And for each position in this grid, we have an estimate to the star formation rate from stacking the far-infrared data and subtracting that estimate from the star formation rate that's based upon stacking of the radio data. And so where we have a positive value, that's an indication that we have radio excess. In other words, that the radio emission is dominated by the AGN. And if you look at the color scale here, we see that for all but 3 of these grid points, we actually have consistency with the star formation explanation. But this picture changes dramatically if we then apply a radio detection threshold to our sources. So if we only consider the sources detected at a 3 sigma level, so remember, this is deep MeerKAT data, and we're still struggling to detect all of these optically near-infrared selected sources. If we consider just those radio detected quasars, then all but 1 of the grid points are consistent with the AGN dominated explanation. And so we can see, well, this, again, the selection criteria we apply is quite vital in terms of the conclusions we draw. But to note that this is still a preliminary work because I'm yet to investigate for this larger sample the fraction of sources that can be truly described as radio quiet versus the sources that can be described as radio loud. And to illustrate that, this is a histogram of the radioluminosities for all the quasars. And the vertical line shown here in gray is just a nominal threshold that was suggested by Kellerman et al. To divide the amount of the radio emission that is due to star formation, so towards the left-hand side here, and the radio emission is due to AGN activity. But again, it's important that we think about the physics that is taking place rather than just applying these nominal thresholds. And so this is something I'm looking forward to exploring further. So having established that the accretion, black hole accretion component is important even in radio quiet sources, what exactly is the mechanism that's taking place? Well, it's possible that we still have radio jets that are present. They're just not as powerful as what we see in those radio loud AGN. Maybe we're not seeing them because our current radio images are not of high enough resolution. Possibly connected to the accretion disk, we have what magnetic reconnection, which is something that we can observe in active stars. And maybe we can draw a parallel here for the accretion disk, and apply what we know about active stars and the relation between radio emission and X-ray emission to these sources. Another idea is that we have radiative pressure from that accretion disk that's generating what are known as quasar winds. Those winds impacting on surrounding medium, creating shock fronts. There's, of course, those shock fronts that accelerate electrons, produce radio emission. So again, another avenue for exploration. And so by constructing large complete samples that are across the radio loud and radio quiet populations, we can start to understand, well, why do we have radio jets being produced in some sources and not others? Is it connected to the availability of gas, or the spin of the supermassive black hole, or maybe the structure of the magnetic fields? So something that maybe we'll only be able to answer with the SK or even beyond. We'll see. So to summarize, at low radio frequencies, we can construct more complete samples of AGN, allowing us to study the different life cycles of these sources. And crucially, we have this legacy sample of the brightest radio sources across the southern sky, which we'd like to observe also both with ALMA and MeerKAT to study that interplay of the radio jets with the reservoir of gas that's available. And we're continually building up spectroscopic coverage for these sources so that the whole community can conduct their own favorite science with these sources. All those catalogs will be publicly available. At lower radio flux densities, we're again considering, well, how much radio emission is due to star formation, how much is due to AGN activity, finding controversial evidence that the AGN is dominating, but at a less pronounced fraction according to the MeerKAT data, because possibly we are picking up more of that diffuse star formation related radio emission. And again, we want to understand the entire AGN population in order to really appreciate how do galaxies grow and evolve over cosmic time. Nkosi for listening, and I'm happy to take questions.
Okay, thanks again, Sarah, for being a speaker today. And so we can take questions from the participants, if there's any. No questions? Okay, I have a question about the plot with the squares that you show as function of redshift at the.
Oh, yeah.
Maybe you can go
The
that to
grid.
that.
Yep. This?
Yes, so you can do only this in Cosmos that has a far infrared coverage by Herschel, right?
Yes. But there's over Cosmos, there's also been some more detailed characterization of the far infrared data. So that's why at the moment it's restricted to the Cosmos field as part of the MIGHTY survey. But MIGHTY covers many more deep multi-wavelength fields. So this will be how we can improve the sample size even more in future. Yeah.
Okay, and this is only this is using the MIGHTY pointing for Cosmos. It's not using the old so you don't have to do follow-ups for this sample, just using the MIGHTY pointing.
This is all, yeah, this is all based on MIGHTY data, yes.
Okay.
which is deeper than previous work.
Okay, and does make sense to make this plot not as a function of the stellar mass and redshift, but maybe changing the x-axis by radio loudness?
Oh, yeah, that would be great. Yes, so that's what I meant about this being preliminary work, that I still need to investigate how many sources are truly radio quiet and how many are radio loud. So
Yeah,
this is it's kind of another area of debate in the literature is not only how you select your radio quiet sources, but also how do you define your radio loudness parameter. And I'm more in favor of a definition that combines both the optical and the radio, because the optical gives you kind of a proxy for how much gas is in the system and feeding the supermassive black hole through the accretion disk. And then you're saying for this amount of gas as input, I get this amount of radio emission as output. So I think that's a more informative radio loudness parameter, and it would be great to indeed look at how this AGN fraction varies with radio loudness at different different stars. Yeah.
Because I did this plot, I did a similar plot with using a radio loudness and the AGN luminosity, yes. And the thing, the conclusion was that there is no so basically there is a complex interplay between AGN and star formation activity. So the radio quiet, what you will call radio quiet in your sample, are restricted to one area on the plot, and the ones that are you will call radio loud are spread because the emission is the radio emission has a significant star formation and AGN components. So you see there is a complex interplay in my plot.
Yes, please send me a link to your work. Be very interested
Sure.
to see.
Yes,
Thank
I
you.
will. Yes, I don't know if there is any more questions. Okay, well, I have another one. To the Z-shaped radio galaxy that you showed in one of the slides at the beginning.
Yes.
Yes, this one. This is light. So so with the MeerKAT observations, basically you can see you can constrain a precision model for explaining the shape of the radio morphology, or you don't need MeerKAT. You need the high resolution data to kind of to create it, to explain that with the precision.
Yes. Oh, it's always the combination of resolution and sensitivity, because you the more of the diffuse emission you can detect, then the better the constraints for the model. And so this is something that's actually a new postdoc at UP is very interested in modeling.
Yeah, because for this source, the precision, it looks like a precision in a precision model scenario. Only the precision just like kind of started or was kind of weak. I don't know how to call it that way, because in other of these sources, they have winds. So the winds are the old radio lobes, and the new radio lobes are rotated, so it has the X shape, right? So you don't have
so
this kind of sources. You don't have this kind of sources in your sample.
Oh yes, lots of them. I just haven't shown them today because we were already quite pushed for time. But please, please do see talks by Kshitij Thorat on X-shaped radio galaxies.
Okay, perfect.
There's another beautiful X-shaped radio galaxy in the Gleam-Podjansky sample. Yeah,
perfect.
I can show you that should be in the backup slides. Oh yeah, that one.
Oh yes, the one is with polarization. Okay, great. Yes, I don't know if there is any more a question. There is time for a question from the participants. Otherwise, we can finish today and say thanks to Sarah again. No questions. Okay, so thank you again, Sarah, and everybody that came today. And we will have a seminar next week as well. But this one is more about cosmology and intensity mapping. So thanks everybody for coming, and see you next week then. Thanks. Bye.